In the course on rheology, we have seen several classifications and several types of materials. We have also observed many material functions which are defined to describe the characteristics of several complex materials. In this set of lectures, we will look at two very important classifications. These are very important because many engineering systems, many material systems which are used in practice belong to one of these categories. For example, cement paste is a very common example of a thixotropic fluid, while several food materials are examples of yield stress materials. And so, quite often it is very important to quantify the nature of these materials, and in today's in this set of lectures we will take a look at what is meant by these class of materials. We refer to them as structural materials because in all discussions related to yield stress as well as thixotropy, we will always refer back to the structural aspects of the material. We will see that the breakup and rebuilding are essential processes that happen when we speak of yield stress as well as thixotropy, and therefore, the structure of the material keeps on undergoing changes during when we are looking at its rheological response. And so, structure is a very important component of defining properties of these set of materials, and therefore, we will refer to them as structural materials. Now, looking at the overall outline, we will start with colloidal dispersions under shear and some discussions related to what happens at particle level, and then define yield stress and look at how this yield stress is present in the material, and we will look at one specific example of Herschel-Berkeley model and then move on to looking at thixotropy in structural materials. We have been following this outline throughout our course. We want to observe material response and we try to classify this so that it is easier to analyze, and we have seen viscous and viscoelastic response, and in the next two set of lectures we will look at yield stress material and thixotropic response. The idea here is to qualitatively first try to describe as what do we mean by this class of response, and therefore, that is what we will do. Parallelly, of course, we try to define a material function because this we can use to quantify the material response, and we define viscosity, relaxation modulus and creep compliance, and in today we will see that yield stress is one example of a material function that can be defined for these materials. Also parallelly we have looked at some simple models which give us an idea of how the response can be, and functional form of how stress or strain rate are related to each other. And so, in this set of discussion where we are looking at yield stress and thixotropy, we will look at examples of Herschel-Berkeley model as well as a structural model. So, now looking at the colloidal system, we know that the particles of colloids are held together because of attractions or interactions between these particles, and as this slide shows that we have what is called a percolating network. If I start from one end, I can easily see that almost all the particles are connected. So, I can start from one end and I can reach the other end where particles are almost connected to each other. So, therefore, there is a cluster of these particles and they are connected to each other through network. And when we disturb this network by applying a shear, when we apply deformation on the material, then the clusters get broken and the particles appear to be more isolated than they are together, as was the case when the material is under rest. So, therefore, we have this going back and forth between these two states. So, we have basically going from flow to rest, we have rebuilding, and similarly from rest to flow we have breaking. So, in many of these situations we will talk of breaking and rebuilding processes that happen in a material. So, if we look at let us say the particle interactions and consider basically that the two particles are next to each other and they are bonded to each other because there is an attraction. So, therefore, these particles are assembled due to interaction between particles, and so there is an energy required to pull these particles apart because they are as if they are connected to each other with a spring. And so, the assembly of particles in such a case is due to interaction between particles. So, now the question is as to what happens to this assembly or what happens to this network of clusters when we apply shear on it. So, if you look at generally the bonds between particles, if these bonds are very fixed or they are very strong, they are very permanent, then basically we will have a solid rigid material. An example of this would be if let us say all these bonded particles are perfectly sintered with each other, in which case they are fused together. So, if particles are fused together, then we know that they cannot separate at all, and in that case the bonds will be permanent, and such a porous structure will have a very solid like response. It will be very rigid material, it is basically a solid material. Of course, what we have is a fluid and then solid particles, and these particles are bonded to each other through interactions, and therefore, it is possible that these particles can be separated. We can have other extreme where the particles do not really have an attractive interaction at all. So, therefore, the bonds between particles are extremely weak or not present at all, in which case the overall response of the material is going to be fluid, because these two particles, though they are neighbors, the particles can easily separate from each other and move about. So, in that case we will obtain an overall viscous response, dissipative response, and therefore, the overall response will be fluid. So, the many materials will not have either of these extremes. So, the bonds between particles will not be permanent, which means the particles can be separated provided sufficient amount of deformation is applied. Similarly, the particles may or may not have very weak bond, in which case there is certain amount of energy required for us to separate the particles and make them move. So, the question that can be asked is, can the bonds be broken when material is deformed? And if the answer to this question is yes, then what we will see is material which was otherwise solid, if a sufficient amount of deformation is applied or the material is deformed to a certain extent, then the material can undergo a transition to a fluid like system. Because if the bonds are broken, then initially material will be rigid, but once the bond starts breaking, it will go more and more, it will become more and more fluid like. So, the natural question that arises is also, is there a critical value of variable, and which variable will that be? And so, is there a critical value of stress at which bonds start to break? Is there a critical value of strain or deformation at which bonds start to break? We can also look at the overall colloidal system in another context. If we have the particle assemblies where particles are together in a jammed state, and by that we mean is basically there are this happens at very high concentration, and particles seem to form chains, and they are forming chains just because they are in neighborhood of each other. So, this chain basically then cannot allow individual particle to move, and even if we try to shear this material, it will resist that, and therefore, this state is called the jammed state. So, because of jamming of these particles, like analogous to what happens in case of a traffic jam, where vehicles cannot move because in the neighborhood there are all other vehicles, and since each vehicle can only move so much, each vehicle is confined because of all its neighbors. Similarly, here also we have a particle basically confined because of a cage. So, each particle can be thought of as being in a cage, and this cage is formed because there are all the other particles surrounding it. So, given that this particle cannot really move out of this cage, we have a situation where the overall material response will be quite solid like, and if the cage is broken, then the particle can move about, and in that case it is possible that the overall response can be fluid. So, in general for particle assemblies, the particles are jammed in clusters, and therefore, very little mobility is there due to the cages being present. And so, the cage particles with no scope of mobility implies that we have solid or rigid material. If let us say the particles are uncaged, or there are particles which are free to move, or they have sufficient mobility, then we will observe a fluid like response, which is of course viscous and also dissipative response. And so, for such materials the jammed states are observed because the interparticle attraction is not a significant factor. So, the particles do not come together because there is an attraction between them, the particles come together because there is excessive population. The concentration of particles is so high that they are forming these cages, and because of the formation of the cages they do not allow motion for each other, and in that case they are jammed. So, therefore, the question that is very relevant for such material systems is if the cages can be broken. If the cages can be broken, then we know that a material in cage state will have a solid like response, but if cages are broken, then we can end up having a fluid like response. And so, the question is whether it is possible for the cages to be broken when the deformation happens. What that implies is if it is possible that when deformation is applied, that there is some rearrangement of the particles would take place, so that it is relatively easier for the particles to move about. Again the question that arises is there a critical value of either stress or strain which causes the cage to break, and if yes, then we can say that at this critical stress the material goes from a solid rigid like material to a fluid like material, or if there is a critical strain at which such phenomena happen, then we can say that material goes from solid like to a fluid like state. And all of this discussion, as we have said, we are only talking about breaking of bonds and cages. So, we can have the cages being broken so that particle can move out, or we can have the bonds being broken so that particles are free to move. So, in both the cases we are talking about breaking of bonds and cages, and this breaking of bonds and cages is said to lead to yielding of material. So, material yields by which the bonds and cages are broken and it becomes more fluid like. So, yield is a concept to try to describe the phenomena where a material which appears to be solid like due to deformation becomes fluid like, and underlying the concept is related to the breaking of bonds and cages. This of course yield is a concept which we look at very often in metals. When we look at stress strain behavior of metals, so if we look at stress versus strain, we know that at small strains we will have an elastic deformation in the material, and where stress is proportional to strain, and also quite importantly, if I increase the stress I will go and then when if I decrease the stress I will come and I will trace the same path. So, if no matter what the stress strain is, the stress is determined completely by strain and strain is determined completely by stress, and so this is the elasticity. But in when we take the material to higher strains, in case of metals what we see is a yield point beyond which we see non-linearity beginning, and the other important aspect is if I release the material, if I reduce the load on it, and therefore it comes back with a plastic strain. And in this context the yield processes are related to crystalline phase in the material, and they yield. So, there is a flow of crystalline material due to various defects. It could be across due to defects which are present at the crystal grains, it could be due to the point and line defects which are present within the crystal itself, So, what we say is beyond this strain the material yields. And or the material also is set to flow, while below this strain the material is elastic and stress and strain are proportional to each other. So, this concept of an yield stress is what is used here also. So, the stress at which yield happen is also called the yield stress. And so, when we look at many metallic materials and we want to design them for structural application, it is very useful for us to keep the design stresses to be much lower than yield stress to ensure that material does not yield during an application. For example, if steel beam is being used, we do not want it to deform plastically during an application, we would want it to remain in this range. So, yield stress is a very important characteristic of solid like materials, and in this case what we have seen is, for example, for metallic materials. And so, we see in this case that there is an yielding phenomena which is associated with the structure of the material. So, we are of course discussing fluid like materials, and in this case the colloidal particles and their assemblies. The colloidal particles are along with a fluid. They are dispersed in a fluid, and this is an example of a multi-phase system as we have been discussing in this course. And so, what we can say is yield this material yields if it shows a fluid like response, the material is below yield if the overall response is solid like. So, therefore, in the materials that we will discuss in this course, we can also define something called a yield stress. So, below a certain value of stress, if the material does not deform, which means it remains very solid like, its strain is very small. The other way of saying this is also that it has an infinite viscosity. This is very important for many of the food, for example, jam. It has a very high viscosity when the material is just scooped out, because it is a solid material, and then when we start spreading it, it spreads very easily. So, therefore, its viscosity decreases beyond an yield point. So, we can talk of many of these materials which we use in the kitchen as yield stress material, that below a certain value of stress they would pretty much be like a solid. Butter also, for example, it will remain like a solid block, but then if we use a knife to spread it, it can be spread, and therefore, it has a finite viscosity. So, below a certain value of stress, the material does not deform, has infinite viscosity, it is said to be solid, and basically either is very rigid, which means deformation is very small, or elastic with very high modulus. Just to remember that when we say a material is elastic, stress is proportional to strain. When we say material is rigid, basically it does not deform at all. So, therefore, the limit of elasticity being extremely where modulus is infinite is what is meant by rigid. So, generally in the below yield stress, we say basically that the material is solid, and therefore, it does not deform or it has infinite viscosity. Above the same value of stress, above this certain value of stress, the material deforms relatively easily, which means it has acquired a fluid like characteristic now. It is either a viscous or a plastic material. It has finite and therefore low viscosity. One key feature that we should try to understand is this notion of viscous behavior and plastic behavior. So, as we saw in case of a metal plastic material, that in this regime we had plastic deformation. So, generally when we observe plasticity in metals as an ideal case, the stress versus strain response is not really dependent on strain rate. Strain rate dependence is absent. So, what that means is if I do the same test at different strain rates. So, let us say if I do stress versus strain rate at two different strain rates. So, I will see that initially the data points will be all elastic. So, they are all in a straight line, and then later on, and then we have the yield point, and so because of the yield point and then there will be a, at a constant stress the strain will continue to increase. We are talking of only strain being plotted here. Now, if I do it at so this is at one particular strain rate. So, this is strain rate 1. Now, let us say if I do the same test for strain rate 2, the strain rate does not really matter in case of elastic deformation. So, what we will see is again we will get essentially the same response, and similarly in this case also we will see the same response. So, basically the stress versus strain behavior in case of metal plasticity as an ideal case does not depend on strain rate. So, then this phenomena is called plasticity. So, this is plastic deformation. If you look at the state here, the stress is not related to strain rate, not related to strain rate. Of course, we call it plastic deformation because stress is also not related to strain. At the same value of stress, which is the yield stress, we have basically the strain keeps on increasing, and therefore, this is called the plastic deformation. On the other hand, when we say viscous deformation, we have seen that for viscous dissipation and for the stress and strain, how are they related? This to answer this question, first you can also think of how is stress and strain rate related. So, we know that for a viscous fluid, and let us take an example of a Newtonian fluid, the linear viscous fluid. In this case, what I would see is that stress and strain rate are proportional to each other. So, therefore, I will only get a basically straight line of response, and so in this case what I will see is as stress increases, the strain rate if as the strain rate increases, the stress also will continue to increase. Given that it is a linear viscous fluid, we would expect the stress and strain rate to be related to each other through a linear relation. And so, if we do now experiment at different strain rate, if the stress is constant and strain rate is constant. So, if strain rate is constant, this would imply that strain will be proportional to time, because strain rate is derivative of strain with respect to time. So, therefore, strain will continue to increase, but at any other stress we will have a different. So, each of these are different strain rates. So, drawing analogously to what we had done in the previous discussion, if we do the experiment at one strain rate, we will get one value of stress. If we do it at a different strain rate, we will get another value. So, therefore, in this case stress depends on strain rate, and this is viscous deformation in the material. So, quite often given that there are researchers and practitioners of different backgrounds working on different set of materials, we tend to use several phrases to describe the phenomena, and we need to be careful and understand the meaning of each of the phrases and what context this is being used for. So, the yield stress as a concept is used by people describing metal plasticity to describe plastic deformation, and we also use this yield stress in the context of fluid like materials to describe the viscous deformation. In both cases the term flow is used or fluid like response is used. However, there is a distinction in terms of what the basic mechanism is and how it is related to strain rate. And therefore, in general when we look at let us say the class of materials which are yield stress materials, we could have their response being described as elastoplastic, viscoelastic or elasto-viscoplastic. So, therefore, these are the phrases that you will hear people talk about when we describe the overall response. So, elastoplastic implying this is before yield and this is after yield. Similarly, elasto-viscoplastic again implying that this is after yield and this is before yield. So, again the materials which have yield stress as the basic characteristic will always have this solid like response and a fluid like response. The fluid like response could be a combination of viscous and plastic type of responses. Whenever there is a strain rate dependency, we will say that it is a viscous dissipation which is the underlying feature and we will call it viscous. When the deformation is independent of strain rate, then we will say that it is plastic mechanisms. And so, we can define a material function in these kind of for to characterize the response of these materials. Basically there are several ways to determine yield stress and we will also soon see that the quantity called yield stress subject to the way it is being measured and quite like in case of polymers the glass transition as a glass transition temperature is not very well understood because we are going from a thermodynamic equilibrium rubber state to a non-equilibrium glassy state. Similarly, the yield stress also is as a material function has there is a considerable amount of uncertainty and there is considerable amount of lack of understanding about what is exactly it means. And so, in this case also we are going from a fluid like material to a locked in cages or clusters which are formed and in that case again whether the material is non-equilibrium and to what extent it is away from equilibrium are questions which are not very well understood. So, from a theoretical point of view and from a research point of view, yield stress as a quantity is still being debated and various people are trying to understand what materials can have yield stress and in under what circumstances we can use the word yield stress for several materials. However, as I pointed out earlier, given that many materials in our day to day applications as well as in engineering applications show this phenomena of yielding, yield stress as an experimental feature or as a material characteristic is used quite often and it is found to be very useful in terms of designing materials and to make decisions regarding what type of material to use or what type of mechanism to use in what type of application. So, therefore, yield stress measurements are done most commonly by applying constant strain rate in simple shear. So, therefore, we do steady shear on the material and when we apply a constant strain rate and let us say for a cone and plate geometry we apply gamma dot theta phi naught and what we do is we measure the stress at steady state. So, we apply a constant strain rate, we wait for the stress to reach a steady value and that value is measured. And this basically experiment is done at different values of strain rate and then yield stress is defined basically the general stress itself tau theta phi will depend on the whichever is the strain rate being applied. So, at different value of strain rates we will get different values of tau theta phi. Now, yield stress is defined as that value of stress when strain rates are very small there is the value of stress which in the limit of gamma dot going to 0. Remember that for a Newtonian fluid, if gamma dot goes to 0, tau theta phi will also go to 0. So, as we expect and as we know, Newtonian fluid is not an yield stress fluid. Of course, it does not have any yielding phenomena. So, therefore, in that case yield stress is 0, but most materials which belong to this yield stress category will have a certain amount of stress even if strain rates are very small, and that stress is called the yield stress. So, in the next lecture we will then see how to measure these stresses using couple of different types of experiments, and then we will also look at the phenomena of thixotropy.